Hello and welcome back to VitoshAcademy. Today we are building a robust k-means clustering algorithm from complete scratch. So what is k-means? It is an unsupervised algorithm that groups data into clusters by minimizing the distance between points and their group center. So what does this mean? You can ask, and the answer is something like this. Just imagine that you have all these points here. It's just a simple search in Google, and you should find a way to cluster them somehow. You can ask yourself, okay, in general, it's interesting. Why is it pretty much, what is it bringing us? Like, how do we decide how many clusters do we have? For example, if we consider each point to be a separate cluster, wouldn't the result be the perfect one? Well, generally, yes, but not the perfect one. I mean, minimal error, but it will not bring us any knowledge. And the idea is to cluster somehow points somewhere. As I mentioned, it is an unsupervised algorithm grouping the data into k clusters by minimizing the distance. Yes, it works assigning points to the nearest centroid and then updating that centroid to the average position of its new group. So to find the best number of groups, we use something called the elbow method that I'm going to present, and you're going to see immediately the difference. And like you're gonna see why it's called elbow method. Then pretty much let's start. So here I'm having matplotlib, and I'm using here something AGG. It is, so to say, forcing matplotlib to work in headless mode, so it saves images to disk instead of trying to render them in a new window, which often crashes with slower computers or large datasets or both, so to say. So first let's get our data. I'm going to make a simple function called read data and file name pass, and I'm going to be calling it from here. Read data, and our file name is actually called unbalance.txt, and let's print our full data once we implement the method. So our data has some points, and I should be coding like a Python guy. Just minimal code. We are not going to think about error handling here. Don't do this in production, but in general it's okay in a video like this, because now we are talking about k-means and not about error handling. So parts, something like this, and this is important because we start appending. Our data is actually integer. I'm going to show you how it looks like, or let's not. I'm going to convert it later if needed. So yeah, this should be enough, and then return points. Let's see. And of course, an error is always happening. Yeah, and we need a list. Okay, this is the fancy data, a list of lists. Fair enough. It is with strings, so we definitely need to convert it to integer, like this. And okay, that's the fancy part. Let's say this way. Okay, integer, and then parts. Okay, this part with the integer should be somewhere here, and the same with this one. Okay. Okay, something like this. Okay, yes. Then we copy it, and then we start closing one by one. Yes. Great, this is the risks of live coding. Okay, what else? We need to filter the data because, well, sometimes we don't need all of this. If we want to run it like 100 times, we better just run it on randomly 2% of the data. So let's go with the filter data. I'm just going to leave it here. And we need points and keep percentage. Pretty much saying how many points and how many percentages do we keep. And if keep percentage, double tapping, tap, keep percentage bigger or equal than 100. Then simply return it. Yeah. Else get some count. Yeah, the percentage will be something like this. Times. Yeah. And now the magic would be random dot sample of points and count. Let me explain what this thing here shows. Does random, let's say, and we need just two. Yeah, you see, random.sample is magic, and it's built-in and it works. Filter data, let's show something. Okay, then partial data would be filter data, full data, and then 1% print partial data. Yeah, it's definitely way less than this one here. Okay, so far so good. We have read our data, we are able to filter it. We see that, that it's okay. We have showed what this one does, and we are going to view this as a Zen. Okay. Talking about Zen, I'm not sure whether you have seen this. Import this in Python. In general, import this. It should be returning something strange. Why it isn't? Restart. I think my kernel has just died. Nope. Now it works, and this is the set of Python. Beautiful is better than ugly, and the rest you can read them. If you want to impress someone who has just started learning Python, this is a good way. So, hope that you're impressed, and let's continue with our step. Now we're going to discuss the math engine, and we are going to discuss a bit about geometry. So we need to calculate distances to avoid, no, not to avoid, pretty much we need to calculate distances just to see something like if we have like this here, like this is our x, this is our y, and we have 2 points. There is a node mathematical method how to calculate the distance between these 2 points. This is important because we're looking for centroid, and in order to get the within cluster sum of squares and its minimum, we need to be able to calculate distance between points. Fortunately, in 2025, we have more than, I guess, around 23 centuries of history on how to do this. I'm just guessing, but it has something to do with the Pythagorean theorem, although it's not explicitly stated that it's about points, but we're going to use it. So let's calculate distances, and let's make a simple formula. So about the calculating, P1, P2, and the formula is, of course, squared plus the same thing but for the ones. So the difference between these, let's say these two, we take this one minus that one, and then we sum it with this one minus that one. And let's see how it is going to work. In general, for 3 and 4, it should give us a 5. This is pretty much the case. But in our case, it's going to be different. Do you have an idea why? Let's take 0, 0. Okay, let's take 3, 0 and 0, 4. So we're expecting a 5. But we got a 9. Obviously, we have a mistake. It should be 1 and 1, okay. And we didn't get a 5, but we get a 25. So that's really important here. Bear with me. Why do we get 25 and not 5? Because in the original formula, we have something like this. And then we get the 5, but this thing, math square, is really an expensive operation. And generally, expensive things are bad. In this case, in mathematics. So as far as we have to code this one multiple times, probably really multiple times, we better stay with this one as it is simpler. Additionally, it doesn't make a change. On the contrary, the difference between we are squaring everything. We are squaring each part of distances between 2 points, so it doesn't matter. We are just winning from the fact that everything is like that. With other words, if we are measuring distances between points in order to measure the exact position of a point, like finding the centroid, it doesn't matter whether we are working with square distances or real distances. Like if something is far away, its squared value would be also far away compared to if everything else is square as well. It doesn't matter. Okay, let's hope you understood what I just said. You can write me in the comments if you want more explanations. Now we are going to look for the closest centroid. and we pass the points and the centroids. Yeah. So the minimum distance is actually a floated to infinity, which is pretty much the biggest thing. Floated to infinity, is it bigger than this number? Yes. Is it bigger than this number squared? Yes. Is it bigger than this number times 24? Yes. So floated to infinity is really a big one. It's actually infinity. Okay, then we have an index equal to -1, and then we start coding. This is something that I really like in Python, in IC, in enumerate. Just okay, then point, and this is C. Okay, if D is smaller than minimum distance, pretty much this one, the first time it will be smaller, then minimum distance becomes the D and index is the I. What do we return and where? Here, return index and minimum distance. Great. Let's find a way to pretty much test it. For example, let's imagine that we have this thing here. Then we have a point called 1, 1. Is here 1, 1. And this 1, 1 should be closer to 0, 0 than to 10, 10. This is the other one. Yeah, in general, this is what we'll have to test. Here we are passing the centroids and we are just giving a point. So let's test this thing. It should be easy. Test cents. These are the centroids. And we have the 0, 0. And we have the 10, 10. And we have the test point. I mean, I'm just going to write the test points. Doesn't matter. Index. I'm just thinking, I'm not even going to write, get closest. Come on. Centroid, shift and tab. Okay, the points are 1, 1, and the centroids are the test. Okay, get closest, centroid is not defined. Point is not defined. Okay. We only test 1 point. Yeah. So the closest index is actually 0, 0. The first one is actually that one. We can have also, just to see that you understand my point, it can be like that. Yeah. And if we have 7, 7. Yeah. And this is pretty much the distance squared. Yeah, fair enough. Yeah. Somehow it works. Just remembering not to do it that way. Hope you understood this one. Now let's go with the call logic, and the call logic I'm just going to write and you're going to wait a bit. Okay, so hope the waiting was worth it. For you it was less than a second, I guess. For me it was a bit more, but here is pretty much the algorithm itself. Let's go this way. And this one is not code, it's a markdown. You mean core algorithm? Okay, don't. sometimes I cannot decide which one to have. Well, okay, now we're perfect. So what do we have? So init random. Init random is rather simple. It returns a random sample that we just showed. So picks a random starting point. Assign clusters is a different one. It is a function that groups points by their nearest center. Then we have here the function for update centroids, which moves the center to the average position of the group, as simple as that one. So let's combine these steps into a loop and see what happens. That's the main loop. K means algorithm. So we need the points, we need the K, and we need max iterations, not more than 100. So our centroids are here. Init random points and K. I really, just opening a parenthesis here, I really like the fact that in Python in general, in programming, I consider it a good practice always to use the same names for a function. Like we are passing here points and K, we are getting here points and K, and we are returning something with points and K. We don't say K here, N here, B here or something, so you forget about it after a second or an hour. So for something in range max iterations, we're going to iterate that many times. So clusters in WCSS, which is within clusters sum of squares, our targets to be minimal. Here we're going to assign clusters, and we're going to use these two here. You see, this is how it works. Then we need new ones, and date centroids, and then clusters. Okay, then if the new centroids are equal to the old centroids, then break. Otherwise, centroids equal to new centroids. And then let's return clusters, centroids, and WCSS. It works. So the idea is that we iterate 100 times. We assign the clusters, change the centroids, and the idea is to make sure that we get the maximum thing. Like update centroids, this is the interesting thing. For example, we calculate the mean of x and y, so this is pretty much the interesting value. We consider each point important, so we don't have weights on the points. I hope you get my point later. So now let's discuss the elbow method. Before, as I promised at the beginning, before we run the final model, we need to find the K, which in other words, how many centers do we look for. In the test case, if we have 100 points, the minimum error would be on 100 case, but it wouldn't bring us any information, like zero information. So we use something called the elbow method. We run k-means for k, let's say from 1 to 10, and plot the error, and the error decreases as k increases. This makes sense. And we look for something called elbow, the point where the curve bends and flattens out. This is our optimal k, and it is going to be saved. Okay, I am going to write this one for you, and you're going to wait a bit, just for a second. So now we have the elbow plot. Pretty much we give the data, and we have something called max k. We are going to run it. There is some b here. We are going to run it. on our data, just reading it again, then filtering it, just so you get my point, up to 20, and then generate elbow plot. Let's write 100, just to see how it looks like an elbow. We would be having max key of 100, enter. And now we should be waiting, because we would be seeing 100 case. Fortunately, the data is just a subset, which is good, just 20% of everything. And okay, 100 was not the best thing. What is happening? Well, you are thinking, I'm going to explain. Pretty much we see with k equals 1, we get this error. With k equals 2, we get this one. And you shall see that with each one later, the error becomes less and less. Okay, not that much, but here with k equals 1, we have a huge number. Then k2, we have a smaller one. And if we wait just a bit more, we shall reach 100, and we shall be able to plot also the whole thing, this elbow curve PNG. And I'm going to show you how it looks like. Yeah, don't do this at home, especially not on so big data. Like if you have written like 2% here, not 20, it should have flight. But okay, we are now on 91. So you see the numbers are less and less and less. But what does it mean? What this error is saying to you? Well, this is just a sum of the distances of all the points when we have a given number of centroids. And let's see now the elbow curve. I'm ready with it. And you see, the idea is it looks like an elbow. Ta-da! And I think that on our data, okay, from 1 we are with this many errors, with that many. Yeah, it's obvious. I think here on 4 it's already okay. So it's either 2 or 4. I would go for it. Let's rewrite it a bit more, just for better visualization. Let's use 10. Run it again, and it's flying this way because we have only run it like 10 times. And the elbow curve, ta-da, looks like this. Okay, it's visible. I would say 2 or 3. Okay, with 2 it's a big fall, and then it's pretty much an elbow. Yeah, I'll run it probably for 2 and for 3. And now the big results. So we pick our k manually, and with the algorithm with random restarts, pretty much random restarts means running 5 times and keeping the best. We need to ensure the best accuracy, and let's generate the code. Again, I'll generate it for you so you don't waste your time. Let's wait a bit. And here is our function. Plot results. It is working. We're passing clusters, centroids, and k. These are the possible colors: red, green, blue, cyan, magenta, yellow, orange, purple, brown. And then we find a way to put them here. We're going to run first with 2 keys, means 2 centers, because of the elbow that you remember. Then we're going to try with 3, just to see the difference. Yeah. And at the end, we are going to see how it looks like. Okay. So 6 restarts, the best WCSS, which is pretty much considered error. Like the best minimal error is this one. And let's take a look at the k-means final with 2. It looks like this. Okay, the centroids are 2. It's obvious. What will happen if we say 1, 2, 3, 4, 5, 6, 7, 8? Would it work as we expect? Let's try with 3. Yeah. Wait a bit. This is with 3. 1 here, and there. And let's try with 8. Because we had, with other words, 8 really big ones. What will happen? I think it wouldn't happen what you would expect to happen. Yes, you see like 2 here, and then 1 here, and plenty of others here. Well, let's try once more. It can be like a difference, because after all, there is like random assigning, and it's questionable whether it would be the same. Yeah, it is not the same. We have 1 here, 1 here, so 3 to the left and plenty of others to the right. But the idea is that using the elbow, if we use 2, the data will always look like that. Like no difference in anything. So this is what we need. Great. Let's summarize. We imported matplotlib. I'm using here aggregate. Why? Because when we work with a lot of data, our computers become slower, and it's better if we save it instead of displaying it. So reading the data, filtering the data, printing it. Here the Euclidean distance squared. Why do we need it squared and not simple Euclidean distance? The answer is the simple distance is too expensive. We need a square root there, and here it's okay. As far as everything is squared, no one cares. Getting closest centroid. Yeah, here we made a small test between 0, 0 and 10, 10. The closest centroid to 1, 1 is the 0th one here. K-mean core algorithm, the core functions are initiating the random, because we start with a random, then assigning the clusters and updating the centroids. Fair enough. Then the k-mean algorithm here, and generaling the elbow plot that I was explaining about. Just showing it once more. If someone asks you what is this elbow method, you can always say, well, if we try with all the means and we plot the errors, there is a position where there is a big difference between error n and error n plus 1. So this is exactly the number of k's that we should take care of. And here the number of k's is 2, because we see the difference, it's visible. And I think this is a good answer. Then we read the data, and at the end we run it with with 6 restarts. We can use 10. Yeah, not a big deal, just running it 10 times, restarting 10 times. And at the end our data looks like this, just with 2 centroids. Rather perfect, no one can tell you anything. Yeah, the elbow method works. So far so good. That's all from VitoshAcademy. Enjoy the rest of your day or night. Take care of yourself. Like and subscribe if you want to get new messages about this one or similar videos. And that's all from me. Goodbye.